Okay, in this video, I'm going to go over the last two questions from paper 2, the 2014 Specimen paper from the IB Math Studies exam. This is a probability question, number 5, probability and Venn diagram. About 50 students that were asked how they traveled to school yesterday. And we're going to represent the information given to us on a Venn diagram. To get the full marks, you need to show the universal set as a rectangle. We need to show 3 interlocking circles inside because we've got 3 modes of transportation. And you should notice that it says all of the students traveled by bus, by car, or walked, which means none of them are outside of the circles. But nonetheless, we need to show the universal set. Okay, we've got a circle for car, a circle for bus, and a circle for walk. And then let's fill in our numbers. 12 students traveled by car only, 7 by bus only, 5 by car and walking but not bus, 10 by bus and walking but not car, and then 3 who use all of the forms of travel. And now these students might be taking, a car for part of their journey and walking for part of their journey, so that's how they're managing to do both on their way to school. Okay. There were 28, moving on here, there were 28 students who used a bus to travel to school. Great, that's going to help us fill in our last missing piece in the bus circle. I'm guessing that's what question B1 wants from us. Calculate the number of students who traveled by car and bus, but didn't walk. That's here. To calculate that, we want to do 28, which is the total bus number they just gave us, minus the people in the bus circle that we've already got, which is 3 plus 10 plus 7. So 28 minus 20 is 8 students. So I can fill in an 8 in that part of the Venn diagram. Then moving on, calculate the number of students who traveled by car. Easy enough to do. Now we've got them labeled. 12 plus 8 plus 5 plus 3. These are all of the people in the car circle, which is 28. Okay. Going on to probability. Tamako used a bus to travel to school yesterday. So we know that she's in that circle of the people who used a bus. Find the probability that she also walked. This is called conditional probability. This is the probability that something happens given that something else already happened. Okay, so the probability that she's a walker, knowing that she definitely took the bus. It changes your denominator, okay? The given that becomes your denominator. So given that she rides the bus, she's got to be one of those 28 people who took a bus. What's the probability that she also walked? So the numerator is going to be the walking people within that bus circle, which is 3 plus 10. So the total is 13 over 28. That's the probability. And then 2 students are chosen at random from all 50. Find the probability that both students walked. Okay, this is going to be a probability fraction for the first student multiplied by a probability fraction for the second student. So what's the probability that the first student walks? If you reach into this batch of 50, pull out a kid, the probability that they walked is going to be, and we don't have on our circle, we don't have that missing piece filled into the walk circle, but we know that these are the people who didn't walk, right? Since there's nobody outside of the circles, we subtract those people that I just put a box around, we'll get the number of people who walked. So 12 plus 8 is 20, plus 7 is 27, and 50 minus 27 is 23. So there are 23 people that walk. So if I reach in and pick a student out at random, the probability that that person walked is 23 out of 50. Multiplied by, unfortunately, the next one is not as easy. It's not just 23 out of 50 anymore. I'm not going to reach back and get the same student. So I'm choosing 2 students at the same time. So the next one is going to be out of the other 49 kids there, how many of them would be walkers? Well, if I just pick one out that walks, now there's only 22 left in a pile that walked. So now I'm going to multiply the first student's probability by the second student's probability. You can leave your answer as a fraction. It'll be 506 over 2450. Or you can do it as a decimal to 3 significant figures. You could even go and turn it into a percent, but I'd rather you just leave it like that. The fewer steps we do, the less error we're going to have. Okay, and then the last one. Find the probability that only one of the students walked, if you're picking out 2 at random. For this one, it's going to be easiest if we do a tree diagram. So I'm going to show you the tree diagram for this one. And it is, let's see, on the exam, this particular part is worth 3 points, so it's worth it to take the time to do the tree diagram. So basically, when we reach in and pick out a student, this question is asking, they either walk or they don't walk. we don't need to put the bus and the car on this tree diagram because the question's only asking us about walking versus not walking. The probability that somebody walks, if we just pick out one random kid, is 23 out of 50. The probability that someone doesn't walk, if we just pick out one random kid, is 27 over 50, right? The two numbers on that tree should always add up to 1. Okay. Now, given that the kid walks, so we're moving on and picking our second kid. First kid was a walker. If we go in for the second kid, the probability of getting another kid that walks would be 22 out of 49, the fraction we just figured out. Or the probability of getting a kid that just doesn't walk would be 27 out of 49. Again, that should add up to 1, which it does. 27 out of 49 because it was 27 kids that don't walk from the beginning. But now there's only 49 to choose from because we just took out a walker. All right, off of this branch, we're going to have walk and not walk. Okay, so what if we pick our first kid, they don't walk, and now we're picking our second kid. Probability that the second kid walks is still 23 because there's 23 kids that walked. We haven't picked one of them out yet, but only 49 kids to choose from. And then the probability of not walking, well, there'd only be 26 of them left and 49. Again, that adds up to 1. Okay, so now we've got to figure out which branches we're talking about. So 2 students are chosen at random. Find the probability that only one walked. So we're adding 2 different branches together. We're adding together this probability, right? A walk followed by a not walk, and this probability, a not walk followed by a walk. So only one of the students walked means we either have a walker followed by a non-walker, or a non-walker followed by a walker. And we need to calculate those 2 probabilities and add them together. So the problem is going to look like 23 over 50 times 27 over 49 plus 27 over 50 times 23 over 49. Double check my answer key, make sure that my answer is coming out right. Looks like it will. Okay, and this is going to come out to, as a fraction, 1242 over 2450, and if you turn it into a decimal, 0.507, the probability. Okay, so it is a lot more work when you have to do one of those tree diagrams, but I think it's really helpful for understanding particularly this kind of, one option is both students walk, and that's not hard, but if you're trying to find the probability that one does and the other doesn't, this is when your tree diagram is going to be really helpful. Okay, and the final question on paper 2 was a big, long, 3-dimensional geometry and calculus problem. Okay. Nadia designs a waste paper bin made in the shape of an open cylinder, volume of 8,000. Nadia decides to make the radius of the bin 5. Great, I can label it 5 right on the picture. Calculate A1, area of the base of the waste paper bin. So this should be nice and easy. Area is going to be pi r squared for a circle. So area equals 5 times the radius squared, which is 25 pi, which is approximately 78.5. Units are centimeters squared. Okay. I could accept 25 pi as the answer, but we're going to have to use it going forward. We might as well get it to 3 significant figures here. Okay. Calculate the height of Nadia's waste paper bin. Now we're going to need to use our volume that they gave us. So the volume for a cylinder is the area of the base, which is pi r squared, multiplied by the height. And now we know that the volume is 8,000. We know that pi r squared came out to 25 pi. And we're calculating the height. So we're going to take 8,000, divide it by 25 pi. We should use our unrounded version. I know I said we should round our answer to 3 significant figures in the first part, but we really should use our unrounded version going forward, or you can reuse 25 pi and calculate h, then round h to 3 significant figures. So h is going to come out to 102 or 101.859. 102, and this unit is just centimeters, not centimeters squared, because it's just a height. and calculate the total external surface area of the waste paper bin. So I would look in my formula book for the curved part of the cylinder, and then add the bottom, because there's no top on this thing. I don't need to add a circle for the top, but I want to do the curved area plus 1 circle for the bottom. So the surface area is going to, the total surface area is going to be the circle from the bottom, right, 25 pi, plus the curved part, which is 2 times pi times the radius times the height. So 2 pi radius, and then our 101.859 ... Again, use your unrounded answer going forward so that your area has the correct number of significant figures. Usually you can get partial credit or even full credit if you use your rounded version, but it's best if your answer just matches their answer completely. Their answer is always obtained using the exact non-rounded version. All right, if we do this and then round it to 3 significant figures, it comes out to 3280 centimeters squared, because this is an area calculation. Okay? State whether Nadia's design is practical and give a reason. If you think about 5 centimeters, that's a pretty small circle at the bottom of your trash can. And then 102 centimeters is pretty tall, especially when you're comparing it to a 5 centimeter radius for the bottom of your trash can. It's basically 10 centimeters across the bottom, but then 100 centimeters tall. It's 10 times taller than it is wide across the bottom. So this is just sort of a reasoning question. It's worth 2 marks. I mean, you get a mark for saying that it's not practical, but then the second mark is given for having the right reason. And the reason is that it's too tall for the radius that you have. So you're going to want to say something like, no, it is too tall, either too tall given the radius or too tall / narrow, right? It's narrow because the radius is so small and the height is so tall. Continuing on to Marin's cylindrical waste paper bin. She wants to keep the volume, but she decides to fix the radius at the base so it's not so small. So that the total external surface area of the bin is to be minimized. She doesn't want super tall, skinny one. So she's going to change the radius. Let the radius of the base be r and the height is going to be h. We're going to write down an equation in h and r using the given volume of the bin. All this means is 8,000 equals pi r squared h. Okay, it's just a 1-mark question. Pretty sure everybody would get that one right. 8,000 equals pi r squared h. They're having me set that up because we want to use it going forward. All right, this symbol came out wrong. This is supposed to be pi here. Okay. Show that the total external surface area of the bin comes out to that. Now, if you can't figure this one out, you can always use that answer that they gave you going forward. That's why they gave it to you there. But we should be coming up with our total external surface area equation on our own, and it should come out to the same thing as what they got. So let's see if we can come up with a total external surface area equation in terms of the radius only. So I'm going to go up here where I have a little more room. The surface area of a cylinder, of this particular cylinder, which is open on the top, is going to include the curved surface and the bottom. The curved surface is the harder one. The bottom is just pi r squared. We know it's a circle. The curved surface, which we would get from our formula booklet, is 2 pi r h, right? We just used that in the previous question. The issue with this is that we can't have a surface area have 2 variables in it, the radius and the height. But we can replace the height with an expression that comes from our answer to part C. So if you take your answer to part C, get h by itself. And the reason I know, by the way, the reason I know I'm supposed to do this is look at their answer. Do you see an h anywhere in their answer? I do not. So I know that I can't have h in my answer either. So I'm going to use my answer for part C. Divide both sides by the pi r squared. And 8,000 over pi r squared is the height. I'm going to plug that into the surface area equation that I'm writing. Actually, I don't really need to write it as an equation. It says I can. Oh yeah, I guess I will. Okay, area equals pi r squared plus 2 pi r. In place of h, we're going to put 8,000 over pi r squared. And then we see if we can simplify this to make it match what they have. So this pi and this pi will cancel each other out. This radius is going to go away with one of these radiuses that we have at the bottom. And 2 times 8,000 is 16,000. So area equals pi r squared plus 2. Nope, sorry. 2 times 8,000, I just said, is 16,000. So plus 16,000 over. There's only a single r left at the bottom. It used to be squared, but it canceled out with the r that was in front of that fraction. And so now we see that our final answer matches their final answer, right, which is over here. This is supposed to be pi. It's just a typo. Okay. Going forward, write down dA dr. So we need to take the derivative of the area equation that we just found and that they gave us. In case we had gotten it wrong, we have the answer. So dA dr, the derivative of our surface area equation. We'll bring the 2 down, which is our exponent, and multiply it by the pi that's in front. That gives us 2 pi. The exponent of the r is going to decrease to just a 1, so 2 pi r. And then I like to think of 16,000 over r as 16,000 r to the negative 1. So when I bring down the negative 1 in front, it becomes minus 16,000. And the r becomes r to the negative 2nd power, which is over r squared. That's a 3-point question. So if you're good at finding derivatives, it's great. You're going to get some good points in your calculus questions. We didn't even have to do anything with it yet, right? Just find the derivative. Okay, here, that's our answer to E. All right, now we're going to find the value of r, which minimizes the total external surface area of the waste paper bin. So minimize means set the derivative equal to 0, right? Because you're looking for a place where the slope of a function is 0. So set the derivative equal to 0. 0 equals 2 pi r minus 16,000 over r squared. We should be able to solve this thing without a calculator. It seems interesting. I'm just looking at my answer key. I see something a little funky. So set your derivative equal to 0. Yeah, I see what's happening. Okay. I can solve this one. I'm going to go down where I have some more room, show you the work for solving it rather than just taking out a calculator to solve it. I'd probably add the fraction to the other side since it's negative. Now I have this. Now I'm going to multiply by that r squared on both sides, which over here will make it become, pi there, make it become r to the 3rd power, and then it goes away from the left side. Let's set this thing equal to 0. 2 pi r cubed minus 16,000 equals 0. So my fraction's gone away. It's a little easier to solve it now. I could factor out a 2. And then at this point, I'm just going to ignore that 2. Move the 8,000 to the other side. And now to solve for this r, I'm looking for the cube root of 8,000 divided by pi. If you have a numeric solver that you feel confident using, or you wanted to try doing this graphically, you could also do it that way. But I don't think the algebra is beyond the scope of what you've learned, so you should be able to find the radius that way. It comes out to 13.7 if we round it to 3 significant figures, and that radius is in centimeters. That's a much better radius than the 5 centimeters that the previous person was dealing with. And so there's our answer for F, or F1. F2 says calculate the value of h that corresponds to this value of r. So we're going to use this green equation that I wrote for h over here. So 8,000 divided by pi. In place of r, I'll put that unrounded version of that 13.7, which is 13.656, rather, and that's squared. When you put that into the calculator, the height comes out to also 13.7 if you round it to 3 significant figures. You would start noticing that this is a trend. I mean, to look for the greatest volume and the lowest surface area, you're going to get a nice symmetrical shape. All right, and then determine whether Marin's design is an improvement upon Nadia's. Give a reason. I mean, it doesn't really have a clear answer in the answer book, but as long as your reasoning makes sense with your answers, so you're going to get follow-through marks here for having a reason that that's backed up by your math. For us, the answers that we just got, yeah, this is an improvement. The radius and height are closer in length. So now it's not like too tall or too narrow, because the height matches the radius pretty well. So you've got a nice wide, round, cylindrical trash container. Okay, and that is it.